Welcome back, everybody. Welcome back. You notice that tonight we have a welcome reception. I'll have more information about that before the next talk after the coffee breaks. But right now, it's my pleasure to introduce Brian Williams, who will talk about a higher Segal Sugawara construction.
Thank you very much for the organizers for inviting me to speak. It's very exciting to be back in South Bend. So I'm going to talk about a higher dimensional version of what's called the Segal Sugawara construction in conformal field theory. So thankfully there's some talk already introducing some rudimentary vertex algebra theory, so I won't review that too much, but let me just review the sort of basic, some of the basic ideas here that I'm positing to generalize. So the point is that the stress tensor in 2D CFT has an infinite dimensional symmetry. By a very important Lie algebra called the Virasoro-Lie algebra. And this is a central extension of, it's called the Wick algebra, which is nothing but vector fields on the punctured disk. Could be formal or algebraic disk. I'll be agnostic for a little bit about that. And in fact, it's the unique non-trivial central extension of this Lie algebra. And the game for finding stress tensors sort of mathematically reduces to finding representations for this Virasoro algebra. Stress tensors correspond to representations and vice versa. And the sort of most basic conformal field theory, which has such a stress tensor, is called the free boson. Can you guys read down here? It's okay. The Segal Sugawara refers to usually more general CFTs than just the free boson, refers to actually higher WW models, which we talked about in the last talk. I'm just going to focus on basically the U1 version of WW here, which I'm calling the free boson. So the sort of field theoretic description of this is as a sigma model of maps of sigma into the circle. And it's equipped with the following three actions. Which I'll write in a holomorphic way like that. This is the simplest free conformal field theory. It's a full conformal field theory in the sense that it has both chiral and anti-chiral solutions to the equations of motion, holomorphic and anti-holomorphic solutions, but they more or less split. So I could just look at the chiral part, just the holomorphic part. That's what's captured by the theory of vertex algebras that was introduced in the last talk. And the chiral part of this system has a single field, which I'll just call alpha and Z. And you can identify just this with roughly the holomorphic derivative of this free boson.
It's important that the target is a circle, not a line.
So sort of not for me, non-perturbatively, you should take it to be a circle, but basically everything I'll say will be just about a line. Yeah, that's a good point. I'll say a little bit about what maybe to do in general in higher dimensions, but certainly in higher dimensions, I'm only going to access the perturbative part seriously.
Also another to say what Del and Del Mars, does it mean like S1 inside C or how do you like how does?
Yeah, exactly. So view this as a sitting inside C, so that these are just the usual 1, 0 and 0, 1 parts of the Durand. Yeah. So the chiral part of this is a field alpha. This looks like a holomorphic one form sort of field, and it satisfies the following operator product expansion. But it's a little different than the beta gamma systems that appeared in the last lecture. Those are another free system. This is somehow even more basic than the beta gamma system. There's only one field. So the basic, very, very basic form of the Segal-Sugawara construction is the following statement, is that there is a one parameter family of stress tensors, or that is conformal structures. You want to say in terms of conformal geometry. And these are governed by the Virasoro fields. This is this field that was called L of Z or T of Z in the previous lectures. This is the thing which corresponds to this vector fields or their central extensions. So this, I'll call it T. It's a one parameter family, so it depends on a parameter lambda. That's just a complex parameter. And it looks like this. So it splits up into two terms. The first term is totally fixed, doesn't depend on lambda at all. It uses this slightly annoying normally ordered product, but that's how I get a field in vertex algebra land. I'm not going to be too fixated on that. So it's something which is first quadratic in this field alpha. And then there's another term which is, so it involves a single derivative and a single parameter here. Actually, this family of stress tensors appeared in or part of this family appeared in the last lecture in this. I think it was called a sort of Fagan term in the stress tensors. Fagan-Fuchs term, thank you. So I told you that there's a correspondence between representations for this Virasoro algebra and stress tensors. So a very important characterization of a representation for the Virasoro algebra is how this central term is acting. It's called the central charge. There's a corresponding family of central charges here, which of course depends on lambda. And it's given by 1 minus 12 lambda squared, so some explicit form. Okay. This sort of conformal structure on the very simple CFT, of course, underlies a lot of constructions in conformal field theory. And part of the goal in a lot of my research is to generalize these constructions to higher dimensions. Yeah.
Sorry, just to clarify, lambda is a complex parameter.
It's just complex here, yeah. Thanks. But I don't mean to generalize in the direction of higher dimensional conformal geometry. I really care about higher dimensional complex geometry. So there's this accident that happens, of course, in 2 dimensions, that conformal and complex structures are more or less the same. I'm not going to be going in the direction of conformal geometry in higher dimensions. I'll be going in the direction of complex geometry. So here's a rough plan for my talk. So first, I'm going to introduce these higher Virasoro algebras. And by that, I mean higher dimensional generalizations of this central extension here, where I replace vector fields on the one disk by vector fields on the n disk. I'll take it to mean the punctured n disk, like here I took the punctured one disk. There's other things you could do. To talk about sort of 3 bosons in higher dimensions, and then third, I'm going to give this Segal-Sugawara construction with some applications. Cool. So like I said, the first step for constructing these Virasoros is to nail down what I mean by the higher dimensional Witt algebra. So vector fields on the punctured n disk. There's a sort of a problem here. So if I try to naively generalize the punctured one disk to the punctured n disk.
I'm confused about when you talked about DDA there, isn't it a 2-disk? In the previous
Oh, it's a complex one disk though. It's complex one dimensional.
Oh,
yeah. So like I said, I'm always going to be in this polymorphic category.
complex n disk, you mean the Cartesian punctured complex n disk means Cartesian product of n copies of C cross?
No, I could mean that, but I mean this.
Wait, but by dn, do you mean v times d times d times, is it a polydisk or is it a?
Yeah, this is a polydisk and I'm subtracting a single point. So that's what I mean by the punctured n disk. Yeah, so polydisk minus a punctured. You're totally right. I could mean take an n-fold product of these things. I won't do that. There is a Segal-Sugawara construction for that sort of object too. This all sort of falls under the umbrella of factorization algebras. You can access both of those from the same object. But I'm gonna mostly just emphasize this case. But there's a problem, maybe even before talking about vector fields, if I just want to talk about functions. And there's a problem which is has to do with a nice accident again in complex dimension 1, which is that the punctured disk is affine. This thing is no longer affine, therefore, and in fact, its functions are just isomorphic to its functions on the n disk without a puncture. And this is a statement which is true for n bigger than 1, and it's true for sort of any meaningful thing, anything I would mean by functions here. So holomorphic functions or algebraic functions or formal power series all have this feature. This is in the original thing I said, holomorphic functions, this is called Hartog's thing. So the idea is not that crazy, it's to instead consider, so clearly by looking just at functions, we're missing out on a lot of information. Well, we know what to do when we have something which is not affine, we should look at its derived section. So I want to replace functions on the punctured n disk by the derived global sections of the sheaf of functions.
But now it does matter whether you're working algebraically or formally.
It does, yeah. So there's going to be versions.
Should we know which version or should I just keep?
No, I'll tell you which version I'm using, yeah. When I read this, I think I mean formal. So let me stick to that for now. So in a beautiful paper related sort of in the construction of so-called higher dimensional Kac-Moody algebras, which are the sort of Kac-Moody analogs of the things I've been talking about, or I'm trying to talk about. Peyote, Hennion, and Kapranov came up with a very explicit model for this derived global sections as a commutative DG algebra. So this is just some thing in the derived category. There's no like unique sort of model, but they constructed a useful model. And let me just say a few words about that. It's called A of n. So this thing, in being a model, it's quasi-isomorphic to this derived global sections. And you should think about this model right here as being, I mean a formal thing here. So this is the sort of replacement in complex dimension 1 for Laurent series. That would be the formal thing. So this is the formal thing. There's also just a purely algebraic thing, maybe to differentiate the notation. I think they even use this notation, square brackets n. And this is the analog of Laurent polynomials. So just C adjoin 2 parameters Z plus and Z minus. This algebraic thing is nice because in the model that they use, it embeds inside of another model that we like in the world of complex geometry. So more of like a smooth category. And that is the Dolbeau complex of C to the n minus 1. So if you're happy just working in this sort of analytic category, you should totally just use this model. It's fine. But I'm just pointing out that there's a slightly smaller model if you just care about algebra. This complex, of course, is concentrated 0 up to dimension n, but the cohomology of all of these things is just concentrated in degrees 0 and n minus 1. This model, for example, though, is more efficient than this Dolbeau complex in the sense that it's as a cochain complex concentrated in degrees 0 to n minus 1. So it's just slightly smaller.
So is that a quasi-isomorphism?
It's not a quasi-isomorphism, but it is dense. So it is dense in cohomology. Because there's stuff here in degree n, this doesn't have anything in degree n, but in cohomology, it's a dense embedding.
Degree n minus 1.
Sorry, there's stuff in degree n here at the level of the cochain complex, but in cohomology, They're both in degree 0 and -1, yeah. So yeah, just maybe I'll just say, so as expected, H0 of AN, I'll just use the algebraic model just to be precise. This is the same as just polynomials and n variables. This is Hartog's theorem, algebraic version of Hartog. And then there's stuff in degree n-1. And there's a few ways to identify this. I'll use a way that's sort of close to sort of uses this embedding right here. And I can write this as successively applying polynomial polymorphic differential operators, constant coefficient, to a very particular n-1 form called the Bachner-Martinelli kernel. So this is a kernel which it's a differential form, so it actually lives in here. Which satisfies the following property that its higher residue or integral over the codimension 1 sphere, which in this case is 2n-1 dimensional. So this is just a Dolbeau form. I need to wedge with the holomorphic volume form, but once I do that, I just get. So it's not quite representing the class of the 2n-1 sphere, but this n-1 form wedged with D and Z is the class for the 2n-1.
So what is the whole index of the form? Is BM?
Yeah, oh, sorry, I didn't say Bachner or Martinelli, just two names. So you should think about this as being one higher dimensional analog of the Cauchy kernel. It's relevant to the geometry that I've been emphasizing, namely the punctured polydisk. There's of course other Cauchy kernels that make sense in complex dimension n, namely if I could look at products of C star or something like that, there's a different sort of Cauchy kernel, but this is the one which is relevant to this geometry.
And the notation means that we're talking about differential operators or something like all all polynomials in these DZ1 up to DZN,
I
right?
didn't see where you were looking, I'm like, sorry, you're looking at your screen.
Directly.
Yeah, so I just mean, you could, this thing is of the same size as this. But yeah, you just, you apply successively these differential operators to this n-1 form. And what's not obvious, because I haven't defined any of the models, that in applying those operators, I sort of remain in this subspace. So part of what I'm saying is that the model that FHK cooked up, at least the algebraic version, it's really an explicit subalgebra of the Dolbeau complex. But if you don't care about that, just think about Dolbeau complexes. Totally fine.
Sorry, and you were saying that this is the only cohomology, or?
Yeah.
Yeah.
Thank you. Yeah. Any questions? Okay, so this is all about functions. We had a commutative algebra. I said there's explicit commutative DG models, algebra models. I really cared about a Lie algebra, this Witt algebra. And my ansatz is just to use the fact that on this punctured disk, I still have a trivialization of my tangent model. So to get a model here, I'm just going to use this original algebraic model and then just adjoin the constant vector fields. I know I can do this because I have a trivialization. So I'll define with n. This is now a DG Lie algebra to be A of n copies. And I think about this as having basis these constant vector fields. And then the Lie bracket is just the usual Jacobi bracket. I should say graded. Because I'll refer to it as differential form degree because I'm embedding inside of Dolbeau forms. There's an internal differential form degree. So when you're defining the bracket, you have to be careful about grading. But besides that, it's the usual formula for the bracket of vector fields. So this is some explicit DG algebra. And so like this. This also sits inside an analogy with this Dolbeau complex. I can take Dolbeau on any holomorphic vector bundle, and this sits inside of the Dolbeau complex of a holomorphic tangent bundle. And this is a sub-Lie algebra.
So you did not define the AN, right?
I didn't know.
So, like, I don't have much intuition what does it mean, like usual something on something which I don't know.
Oh, I'm taking for granted that everyone knows what Dolbeau cohomology
Oh, okay,
is.
so you're like taking it inside of that and then you take.
Yeah, so if you don't care about these models at all, I just want to emphasize there's these nice algebraic gadgets floating around if you really want to connect it back to something that looks like vertex algebra theory. But if you don't care about that, just take these Dolbeau models as the sort of DG things that I'm working with. Yeah.
So the Lie algebra structure is really sort of simple, right? It's just in use from the commutative Lie algebra or.
That's how I defined it here, yeah. And then I'm claiming it's compatible with the usual
Mhm.
embedding inside of this Dolbeau complex. So this also has a canonical structure of a DG Lie algebra. It's the same. So what about central extensions? That was really the key thing in conformal field theory. So central extensions. And it's already important, or it's extremely important that we're working in this derived setting. Because as you can see here, by Hartog's theorem, if I didn't do this derived thing, I would be getting nothing interesting. There's no central extensions because I'm just talking about vector fields on the end-disk. There's a simple Gelfand and Fuchs computed some cohomology. You can see that there's no non-trivial central extensions. So this feature of not being affine really forces you to work derived, and when you do, you're rewarded. So there are non-trivial central extensions. So I've produced a map. So there's a map from. I'm just going to basically state the answer. I'm not going to focus on this too much. So there's sort of a transgression map from the Lie algebra cohomology of vector fields on the n-disk. So this is not punctured. I just mean the n-dimensional disk products, the n-dimensional polydisk. I claim that there's a map. There's in fact an injection. I guess this is to the Lie algebra central extensions of this DG algebra. So this is on both sides, this Lie algebra cohomology. You recognize H2 Lie algebra cohomology, that's the thing that parameterizes central extensions. Who knows what this parameterizes? Not so, I mean, L infinity extensions, I guess, of this Lie algebra. But importantly, I'm doing some sort of transgression thing, so the degrees are changing. And I don't know, so in dimension 1, this is an isomorphism. In higher dimensions, I suspect it is too, but I haven't proved that. Kapranov is doing some related things, and he may have already proven this, I don't know. He has a different method of producing these central extensions, which is very interesting. But I don't know if this is an isomorphism, but I do know that it's an embedding. And let me just explain why this is good. It's because, as I said before, you can actually compute this. This goes back to some classic work of Gelfand and Fuchs. So this cohomology has a beautiful description. So I'll just say that in general. So the general cohomology of vector fields on the formal n-disk is isomorphic to the de Rham cohomology of the following vibration. So you take the universal UN bundle, think about this as an infinite Grassmannian, and then I can take its 2 n-dimensional skeleton. That's the real 2 n-dimensional skeleton. And then pull it back. I'm not going to name that space. But I'm looking at the cohomology of this space here. So this is some UN bundle over this 2n skeleton. And the claim is of the theorem of Gelfand and Fuchs is that the cohomology of this space is isomorphic to the Lie algebra cohomology of this Lie algebra.
You know, I was wondering if you replace the width n by this larger model of this Dolbeau complex with coefficients in the tangent bundle, does that change the inactivity or is that?
No, it doesn't.
Oh.
No, there's nothing. Yeah.
So is there? So is there a reason to work with this minimal choice? I mean, the other choice you can write down and explicitly instead of saying, oh yeah, there's some definition of it. What's the advantage talking about the width
For
itself?
me, just to try to write things in a way that's parallel to the theory of vertex algebras, that's really my answer. The constructions I have in mind all sort of work best in an analytic category anyway, that I'll mention later. These sort of factorization algebra techniques work best in an analytic category anyway. But yeah, just the first part of this talk, just trying to say things in a way that's as parallel as possible to, yeah, the algebraic theory of vertex algebras. That's a really good point. Yeah.
There you consider just discrete cohomology or
This is a continuous cohomology, yeah. So there's a topology on this space.
cohomology over the other.
What, sorry, what's that?
Unest.
Oh, I don't know about that name, but yeah, it's just, this is a topological Lie algebra and I want continuous cochains. Look at that cohomology. That's called Gelfand and Fuchs cohomology, or it's the cohomology they introduced. Maybe it agrees with the fancier one that you're talking about. So in particular, simple application of the Serre spectral sequence for this vibration over here tells you that in this particular degree, so here I was looking at degree 2n plus 1, that's the ones that correspond to central extensions of the width algebra. By the Serre spectral sequence, this is also the same as 2n plus 2-dimensional characteristic classes. I'm going to write over here again because I want to make some more points about this. So when n is 1, let's do some examples. I already said when n is 1, this map is actually an isomorphism, this transgression map. And we can identify the 2n, sorry, of course, the degree 4 cohomology of BU1, there's just one thing called C1. And that's the Virasoro cocycle under this embedding here. Let me give you a flavor for how that works. So as an actual cocycle, that is on the Witt algebra, as a 2 cocycle, you can sort of squint and see the appearance of this square of this first term class. So if I'm given, say, 2 elements of the Witt algebra, that is just 2 vector fields on the punctured 1 disk, I can look at the residue of the following quantity. So by this, I mean, by J, I mean the Jacobian. So if I'm given a vector field, right, like Fi Tj, this is a matrix, which is Tj Fi. Of course, in complex dimension 1, these are just numbers, so I don't need to worry about matrix multiplication. And you can see that if you squint, you can see the Virasoro cocycle if you've seen it before. Namely, it's a cocycle which involves 2 vector fields and it's third order and differential operators. So there's 2 here from the Jacobian, and there's a holomorphic differential as well. And I claim if you squint, you can sort of see C1 squared here. It's a product of two things. There's a trace going on, which I didn't need to do because these are already numbers. And there's some transgression that goes on. I only see a single holomorphic derivative because that's all I have.
So Brian, I have a dumb question. That W is about credit. It's not about the class you're integrating against to define the transgression. Right?
This is just in the construction of this map here. Yeah, that's what I'm crediting myself with. Yeah.
Yeah, so it's not the name of a class that you're integrating against.
Oh, no, this is just credit. So, yeah, sorry.
Thank you.
Could we now call it the Williams?
No, because these classes are all, no, I didn't invent characteristics. Anyway, just the map. So when n is 2. So now something different again happens. So we already said in dimension 2, we had to work in a derived way to get anything interesting. What's also different is that there's not a unique version of, so by the way, this is the usual, I said it, it's the central charge. So it's the object which controls central charge. So now I'm looking at H6 of BU2, but there's two things there. So for example, the class C1 cubed, that corresponds to claim an element in H2 of width again. And annoyingly, it's 3 linear, at least the model I know is 3 linear. So let me just explain it. So I have 3 vector fields now, mu0, mu1, mu2. And it goes to the following class. So again, I use the residue. So this was the S1 residue. Now I'm using the 3-sphere residue in complex dimension 2. And I look at trace of J mu0, D trace of J mu1. Sorry, I'm running out of space. D trace of J mu2. Does this look like a 2 cocycle to anyone? I told you it was degree 2, but it looks 3 linear. It is 3 linear. I'm not trying to. But the thing you need to remember is that what's different in higher dimensions is that these also carry some internal degree. So these carry an internal cohomological degree. To integrate against the 3-sphere, I've introduced 2 holomorphic derivatives explicitly, but it's a 3-dimensional object. So I need another degree around, I need another cohomological degree around to integrate, another differential form degree. I need one more, right? Because it's a 3-sphere. So I need this is going to be integrating a 2,1 form. But 1 here carries cohomological degree in this complex here, right? Yeah. And because this is 3 linear, I have to subtract 1 for the internal degree, it's total degree 2. So this thing still has total degree 2, that's why I'm not lying to you, it actually does lift in H2. You can see C1 cubed maybe, just sort of heuristically, there's 3 traces that appear. So it looks like the first 3 first-term classes. Maybe for time's sake, I won't tell you what C1, C2 looks like, but it's a similar formula. So instead of 3 traces, there are only going to be like 2 traces in this expression. Another feature is that they involve 1, 2, 3, 4, 5 derivatives. In complex dimension 1, we had 3 derivatives.
Is the H2 Lie of the width n, is that always 1-dimensional, or what's the dimension of that thing in the examples that you're discussing?
So it's all right, because I can show this is injective, it's at least 2-dimensional in complex dimension 2. But I don't know of a full characterization of this cohomology.
Yeah, so sorry, injective, right? Sorry.
Like I said, Kapranov may as well have already computed this thing totally. I just, yeah. But I at least have this. I have this family of very interesting characteristic classes which sit inside, which determine central extensions. There's a. Just want to make one comment. So there's a geometric way of thinking about these classes here. Maybe I'll start writing over here again. So one way to, so when n is 1, C1 squared, you can think about as labels an important line bundle. Line bundle on the moduli of Riemann surfaces. This is this like Balancing line bundle. So it's line bundle which is produced by some determinant line construction. So in the sense of Quillen. So the way you build that is to take the moduli of curves that has a universal bundle here. Any natural holomorphic vector bundle determines a vector bundle on this universal curve. And I can look at the push forward of this vector bundle down to mg and take its determinant. This is like the Quillen determinant line construction. And this determinant line, or maybe rather its first term class, is what I'm identifying with multiples of this characteristic class here, C1 squared. And you can see why that's true via Riemann Roch. So because this is obtained via some push forward, this thing right here is the same as the integral over this vibration of Todd times CH. And this relative integration is complex one-dimensional, so real two-dimensional. To get a first term class, then I need to start with something in degree 4. Right? So that's where this H4 of BU1 came from. There's only one thing. So all these all line bundles that are produced in this way are their first term classes are related up to a multiple. There's the exact same interpretation in higher dimensions. So I don't even need to change anything. Take this to be the moduli of complex n-folds. It has a universal n-fold over it. To produce classes, line bundles, or to produce first term classes of determinant line bundles via this sort of construction, what I need to look at is H2n plus 2 at BU. That's what's going to label the first term class. I'll be able to express the first term class of such bundles as combinations of those sort of classes. And this is with an eye towards anomalies, which I'll talk about in a minute. This first term class is interpreted in quantum field theory as an anomaly of some QFT. These are anomalies which are sort of gravitational in nature, they're called. This is like really a holomorphic version of a gravitational anomaly. Because I'm not looking at moduli of metrics, I'm looking at moduli of complex structures, but it's sort of similar.
If I could also, yeah, from the geometric perspective, like if you're going to, there's this long-standing issue, the physicists, for them, the Virasoro algebra is just an algebra, but then the mathematicians want to make it into a group. And then there was like period of, but, right, they wrote it down nicely as a group, and it involves the kinds of ideas you're talking about here. But I'm just wondering if I was going to generalize the Virasoro algebra to higher dimensions, I'd start with the Virasoro group, and then you know what I mean, because that's the most foundational thing.
I agree with you. Yeah. I would search for maybe a construction as like a derived group scheme or something, but I don't have anything to say about that. This is all sort of like. This would be the tangent space of that object. That's the sort of thing.
Okay. But I think this thing you just wrote down now is very compatible with that view, though.
Oh, cool. Okay. And any questions about? So these are definition. I guess I'll get the definition. So given a C and H2n plus 2, PU n, the n-dimensional Virasoro algebra of type C is this corresponding central extension. Oh, I just told you that.
That one is, how do you know it?
We could talk about it after.
Yeah.
It's a little subtle.
Yeah. So the others?
What's that?
I mean, do you know exactly which ones are non-zero? Do you know the kernel?
I don't know the kernel. Oh, no, sorry. This map was injected.
Oh, this map was injected?
Yep, that's what I'm saying.
Oh, you wrote.
So there may be more extensions that I'm not seeing, but these are non-trivial extensions. Yeah. Okay. So I'm gonna state without much background, because I think factorization algebras were discussed a bit last week, but there's an upgrade of this construction, not to past Lie algebras, actually to factorization algebras. So I can form higher dimensional versions of not the Virasoro-Lie algebra, but the Virasoro vertex algebra, which is all of Belenson and Drinfeld, a very special type of factorization algebra in arbitrary dimensions. So let me just state it like this. So given any complex n-fold X and C as above, there is a factorization algebra, which I'll call scripty here, C on X. And I'm just going to tell you a bunch of properties that it has. So the first is that this is an example of what's called an enveloping factorization algebra. Which tells me that the value on any open set is the following. So you look at the symmetric algebra on here. Now I'm using Dolbeau forms. So let me just explain this cochain complex. So this is a DG factorization algebra. So to an open set, I assign a cochain complex. And there should be a shift by one and another parentheses. And what this is, it's nothing but a twisted version of the Lie algebra homology of this DG Lie algebra that I just talked about. Except I changed the support condition. So I use Dolbeau forms with compact support. That's one of the main reasons I need to use analytic things. I don't know how to talk about compact support in such an easy way in an algebraic setting. So this is a version of Lie algebra homology. So this is Lie algebra homology. Of this DG Lie algebra. So it's Dolbeau resolution of vector fields, except I demand compact support. So this thing really looks like it's a cosheaf now instead of a sheaf, for example. And I don't just do that, I also twist it. So I twist it by this central charge frame, which I won't say too much about how to do. But this gives you sort of a feeling for what the explicit complex looks like. And when the complex dimension is 1, you'll find that this is exactly the enveloping factorization algebra that Belenson and Drinfeld introduced, or it's at least a model for it in this sort of smooth analytic category. I did that sort of translation between the sort of this smooth analytic object and the Belenson and Drinfeld in some earlier in dimension 1. Okay, here's another feature. So so it's clear that these things are generalizing Virasoro algebras, at least to me. But here's something a little more explicit. So let's look at complex dimension 2. So there I have a 2-parameter family of central charges. So I have this class in H6 and this other class in H6 of U2. And then I can look at the Virasoro factorization algebra on the complex dimension 2 manifold, which is a product of 2 Riemann surfaces. And then I can push it forward along one of them. Let me just assume sigma is compact here. Closed compact. Then the push forward of this factorization algebra. So this is a factorization algebra on C, now just a Riemann surface. Now I'm in complex dimension 1. It's isomorphic to the usual Virasoro vertex algebra, or really it's conformal blocks. at central charge. So 2D central charge, see if I get this. 3 alpha plus beta times the holomorphic Euler characteristic of sigma. So just something to do with the manifold sigma and the parameters I started with. So by, in physics world, this is called compactification. So by this explicit compactification, this is how you can see the usual Virasoro vertex algebra from these higher dimensional objects that I'm cooking. There's only, remember, in dimension 1, there's a unique central charge, so it has to be a combination of these ones I started with. And finally, to tie it back with the Virasoro-Lie algebra, let me just say one more thing. So I can look at a different sort of compactification. So I can look at Cn minus a point. That was the sort of manifold I started this talk with. And I can push forward down to just the positive real line. So that's the radius. This is like the fibers here are equivalent to 2n minus 1 spheres. So pi star of V or C is almost locally constant factorization algebra on R. Say almost, you have to do something, which I don't want to say much about right now, but it's very close to being locally constant. I can at least extract a locally constant piece. So therefore, it's equivalent to an E1 algebra. So in this E1 algebra, or DG associative algebra, is equivalent to the enveloping algebra of this Virasoro-Lie algebra at central charge sequence. So that's this sort of object number. So I look at the enveloping algebra of this Lie algebra, except in general dimension.
But shouldn't it look more quantum mechanics, but not locally constant? Like, surely, your balls of, or say like punctured annuli of different radii.
Yeah, that matters for sure. So I'm saying there's the precise statement is that there's a dense subfactorization algebra, which is locally constant. So that was the thing I didn't want to get into. That basically what you said is like the only thing that makes it non-topological. Yeah. Okay, so I want to start turning to higher dimensional versions of free fields now. So I talked about the very basic free field in complex dimension 1. Now, I'll put bosons in parentheses because they don't always look totally bosonic. So there's two perspectives that I'm going to take here. Two equivalent perspectives. Actually, in the sake of time, let me just do the one perspective. I'm just going to do one perspective. So just to recall the complex dimension 1 case, so there's a sense in which we can, and this was talked about in the last lecture, we can understand this chiral boson here as a particular boundary condition of a three-dimensional theory. That three-dimensional theory is called abelian-Chern-Simons theory. So the chiral boson is a boundary condition of abelian-Chern-Simons on sigma times pi. And it's really that chiral boundary condition that was talked that was addressed in the very first lecture today. It's just in the abelian case. So in real dimensions, four n plus three, there's a nice family of Chern-Simons theories, which are abelian, which generalize this usual Chern-Simons theory of flat connections. And these Chern-Simons theories parameterize flat gerbs. So flat connections on higher gerbs. So I'm just going to think about the real dimension 7 case. So I guess n is 1 in this parameterization. There is a Chern-Simons theory. It's very basic of three forms. So thinking about this free form as a flat connection on the trivial two-gerb. That's how you should think about it. And the action is it's very stupid. I guess maybe let me call H my free form. It's HDH. And of course you can recognize this as just the kinetic part of the usual Chern-Simons differential. So I'm going to now look at the 7 manifold, which is a product of a complex threefold. That's the one I care about. There's something else you can do, which I'll mention, which Witten studied back in his study of fibrates, M5 which had a different geometry, but this is the one relevant for me. So this is a complex three. And then I claim there's a boundary condition where I take the restriction of this three form on x times 0. And because I'm on a complex manifold now, I have a Hodge filtration, and I can just ask that Hodge types which are less than or equal to n and arbitrary anti-holomorphic Dolbeau type vanish on the boundary.
Apologize for which value of n. N is not 1. Or
Sorry, this n is that n.
Same.
Yes.
Which is the.
Sorry, and now I'm doing set. So when n is 1, so the dimension of x is, complex dimension of x is 3. I'm sorry, there's so many. And I require that h.
The n's mean the same n.
The ends are the same. That was like sort of miraculous, actually. For me, like that they matched up. I'll just remark, because it's really, really important in Witten's study of the quantization of what's called the M5 brain, which all of this stuff is, I would say it was motivated by reading this paper. He cares about a slightly different geometry here. So he takes, let me just do the 7-dimensional case to be a product of a Riemannian 6-manifold now. So now there's a Riemannian structure. And he requires that the 3-form H lie in self-dual 3 forms. And he calls so I'm working in BV, of course, so you should really even interpret this H as not just a three form, but really it's a whole de Rham complex on the 7 manifold or n 4n plus 3 manifold. And I shift down, I'm gonna get the shift one. Let me do M7, I shift down by 3. So I have the whole de Rham complex. And on the boundary, what this means is that the free form, or the two form on M is required to satisfy the self-duality condition. That's another way to say this. This is equivalent. And Witten, annoying for me, but not annoying for anyone else, calls this a chiral two form. There's no complex structure around them. For me, there is. So maybe I'm actually studying real chiral things, and this is just it's a very nice analogy with another nice analogy with the chiral boson and CFT. But it's a different one. It makes sense in Riemannian or Lenzing geometry, whereas mine makes sense in complex geometry.
So how is simulated to H?
So it's one of the gauge symmetries for H.
Oh, okay.
Yeah. So like I said, I'm working in BV. So in real dimension 7, I have gauge symmetries which are two forms. And it's a requirement. This boundary condition tells you that that gauge symmetry satisfies some condition, which is self-duality here. This is sort of going back to why. These sorts of two forms come up in M theory when studying what are called M5 branes. This two form does. But it's really annoying because they don't admit a Lagrangian description. This is why they don't admit a Lagrangian description. They satisfy this constraint, which is totally natural from the point of view of Chern-Simons, this boundary condition. To get a Lagrangian subspace, at least, it's obvious why you need to take half of your three forms in some way. I'm taking half of my three forms in another way here. In the complex world, this is how you do it in the Riemannian world. So very explicitly, the sort of the fields on X, which satisfy.
Wait, what do you mean by self-dual? Because the square of R² is -1.
I think I wanted Lorentzian signature here.
Oh,
Yeah,
there we go.
that was what I got.
There we go.
I wanted Lorentzian.
That's
signature.
full, yeah, perfect, okay. Yeah.
I said Riemannian, I'm sorry.
Yeah.
I'm sorry. Yeah, I said Riemannian, I meant Lorentzian.
Yeah.
Sorry. So the fields on X, so now, this was just a remark, by the way. I won't write down a metric. You can't force me to. I'm gonna work in complex geometry.
But it's a conformal invariant, by the way.
It is, that's why this is.
That's why he calls it chiral.
Exactly, yeah. Chiral for me means the other thing, which is. Yeah. So the fields on X satisfying this holomorphic boundary condition. So I'll call it holomorphic to not confuse with chiral. Look like the following. So I have some in degree -1 and 0. I have a 2 comma star form on X, mapping to a 3 comma star. By a del, and internal to all of this, of course, is del bar, which I'm not going to. So I have this half of the de Rham complex on the 6 manifold, which is X. That's this boundary condition explicitly. I'm just spelling out what this condition H means. Satisfying this boundary condition. So there is an easy way to quantize this, at least perturbatively. So I get a factorization. I'll call it observables. So this is factorization algebra of observables on the chiral boson. By that, I mean the thing whose fields are this, for example. So these are the fields. I'm looking at functions on the fields. Those are observables. And I'm claiming that admits a quantization in the BV formalism, which is very easy to construct. And I'll call that props. So now I can state the theorem. So this is the generalization of Sugawara. And let me just state it first, just in this dimension here that I've been emphasizing here. So let X be a threefold, complex threefold. Then there is a map of factorization algebras. Which I'll call T. So these are T for stress tensor. Stress tensor is analogous to the vertex algebra case. They're maps from the higher Virasoro algebra now, higher Virasoro factorization algebra, into observables. That's what a stress tensor is in vertex algebra. It's like an interaction of the Virasoro vertex algebra. I actually have a map here.
Sorry, T sub C? C is a parameter somehow.
Oh, yeah, thank you. So C is fixed here, and I didn't tell you what C was.
Oh, C will later, you'll give us a.
I'll tell you what C is, for some C, and I'll tell you what it is right now. Okay. Where you've definitely seen this class before. I'm just kidding. So where C, so where is it? I'm in complex dimension 3, so that means H8 of BU3. Not as nice as the one dimension. Oh, that very interesting class. So I can compute this in two ways. One, using explicit Feynman diagrams. That's one way of computing this anomaly here. The other way is to use a version of Riemann-Roch in the style that I was sort of emphasizing before. That's the easiest way to get this number, or to get this class here. And the last thing I wanted to say is that so like in the one-dimensional case, there was a one-parameter family of deformations of the stress tensor. Right? That's very important actually in this sort of construction of what are called non-critical string theories. Anyway, the analog here is that there is a two-parameter family of deformations. Sorry, I'm done after this point. And they're parametrized by H2 vector fields on the 3 disk with coefficients in closed 2 forms on the 3 disk. And there's sort of 2 classes here, but let me not say it exactly. But what I will write down is an explicit formula for this. So for every open set U, I can describe T in the following way. So T of mu is given by the following observable. So you integrate, let me just look at a global observable X. You integrate alpha that I contract with mu. So I contract with a vector field here. So that's the first term. This is analogous to the first term in the usual Segal-Sugawara tensor. You can check that this makes sense, that I can actually integrate, because let's just take alpha to be a type 2 form here, holomorphic type 2 form. So it looks like I have 2 of those, so that's like too many degrees, but I contract once with a vector field. So I end up getting a top form, and I can integrate that. And that's identical to the formula that I have in CFT, actually. It's the same formula. And then I can write down this 2-parameter family. Let me just call them alpha and beta inside of here. That's 2-dimensional. You can write it down like this. So it looks like alpha And then, sorry, alpha is a very bad letter. Sorry, lambda 1 and lambda 2. So lambda 1 alpha trace. So again, it's linear in the free field. And then there's another one plus lambda 2 integral alpha trace chain rule. And you can check that those are of the right degree to integrate. And I won't tell you what the central charge is when I turn those lambdas, but it corrects the central charge by terms which are both linear and quadratic in lambda 1 and lambda 2. So I'll just stop by saying these sort of expressions for the Segal-Sugawara tensor in higher dimensions, or at least what I'm calling the Segal-Sugawara in higher dimensions, appear already in a lot of places in physics. So in this five-brain story that I was talking about with Witten, there's shadows of these sorts of terms which appear in the sort of Green-Schwarz mechanism or anomaly cancellation for M5 brains. There's also a version which appears in real dimension 10, so having to do with type 2 string theory. There's a version of the higher Segal-Sugawara construction going on there. But let me not go into any of those yet. I'll just stop. Thanks.
Questions for Brian? Yes.
Sir, so I guess in the question, can this start instead of a puncture disk from a universal torsor over some other toric variety? And get like the characteristic classes of toric bonds?
It's a really good question. I mean, I already in a sense have, like this construction of a factorization algebra makes sense on any complex manifold. So you can apply it to a toric variety. It's a really good question to try to express the one thing you could try to do is to try to express the state of conformal blocks or global sections in terms of the toric data, and try to maybe recover some sort of formulas like you would have in CFT for conformal blocks on a Riemann surface like P1 or something. It's a good question, but in a sense you already have the sort of object you want. But yeah, there's a lot to do. Yeah.
Instead of using Dolbo, what if one tried to use check to resolve this? See any doing? Sounds too horrible.
It doesn't sound horrible. I wouldn't know how to. You mean like check Dolbo, I guess, or
No,
just check.
yeah, but I wouldn't see that it was a Lie algebra, it'd be an L infinity algebra.
For sure, you wouldn't. I mean, here it's also an L infinity. I wrote down a 3 linear thing. I never wrote down the Lie algebra explicitly. I just said it was classified by this thing in H2.
Oh,
The model I have is already L infinity. You're not gonna. Yeah, I don't
I see
think
what you mean. Yeah, but the underlying Lie algebra is a Lie algebra. but
that's
not
also,
Bogart.
yeah, that's true.
This one would, the check one would.
It won't be, yeah, that's already gonna, yeah, that'll be worse.
If you like,
I have a question. So for when in the one-dimensional case, I understand the Virasoro algebra sort of as sort of the quantum symmetry of the free boson, right?
Yeah.
And now in the higher dimensional cases, you can talk about the free boson in that dimension. And then you could ask, what is a symmetry group? So is a symmetry group of that sort of the universal central extension of the Witt algebra N, sort of where the group you're extending by is sort of not one-dimensional, but sort of, I don't know, whatever dimensional?
Again, I'd be hesitant to say anything about group structures, but there is like a universal extension here, which is extending by.
I mean at the algebra level.
Yeah, yeah,
The
there is a
algebra.
universal thing that you just get by extending by whatever H2 of the.
Right. And should I think of that universal thing as being the symmetries of the free
Yeah.
boson in dimension N?
Yeah, definitely.
What is the reason of zooming into a particular sort of something by choosing, say, this funny linear combination of C that you have there? Like, where does this particular extension come from?
Oh, I mean, this is just what, maybe I misunderstood your question. This is just what it is, like. There's no, so the theorem should have been, starting with this stress tensor here, this is like a classical object. I can quantize it almost at the price of introducing a central extension, just like happens in CFT. And it's just, that's the central extension you have to turn on.
I see, so you're saying the symmetry, the quantum symmetry is still a one-dimensional extension of.
It's a unique thing, yeah, exactly.
Oh, I see.
It's a one-dimensional, it's picking out something one-dimensional and
Inside the universal extension.
inside of the universal thing. But then I'm saying there's this modification where I can sort of modify my stress tensor in this way, and I didn't say it in formulas, but this will modify the central charge in a way that's like both linear and quadratic in these parameters. So you can sort of mess around with it a little bit.
Okay, great, thank
And
you.
that sort of messing around appears in the Green-Schwarz mechanism, actually. It's a sort of holomorphic avatar of this Green-Schwarz. So I should say, yeah, this free boson is a free limit of a theory people really love. It's called the topological string, closed topological B model on X when X is Calabi-Yau at least. So this is sort of seeing a piece of the closed string B model, if you like.
So does your theorem hold in higher dimensions? And do you know what C underline looks like?
I do in higher dimension. It's of course different than that formula, but yeah, the theorem is the same with a different value of C. Yeah. So it's just this thing.
And C is always unique.
Yeah, so this expression here makes sense in any dimension, and there's a unique C which corresponds to using this.
I see.
You can sort of see what's going on here, like there's going to be a different space of deformations in general. But again, it's sort of uniform. The approach is uniform.
You want to talk about category of representations of this object, or it's how, I mean, to what extent it exists in a sense that, you know, like you have fork modules and, you know, you realize that German modules, you know, there's a whole.
So I'd like to think about this as like a simple sort of testing ground to try to lift a lot of these concepts in representation theory. Like Chern-Simons is a very simple theory that sort of has this nice higher dimensional generalization. I get these very nice sort of holomorphic chiral objects on the boundary. If there is a higher dimensional or sort of well-behaved representation theory going on, it should be very nice in this setting. But I don't have anything like concrete to say.
There's no like simple model or, you know, basic representation or like Hayek's model.
There's nothing been developed, I would say. Yeah. Like this should be the primordial example of a simple higher dimensional vertex algebra or whatever, this free boson. And you should be able to try to prove some nice theorems about that, but yeah, it's not something that's been developed. I tried giving the first part of the talk very algebraic to try to inspire people to maybe think about the representation theory, because I haven't done it.
I'm sure there are more questions, but let's hold those off for coffee break, and let's thank Brian again. And we'll resume here just a little bit before 4 with some announcements about the reception for tonight. But until then, enjoy coffee. I'll see you back in about 35 minutes.